In this video, we're going to demonstrate some of the gas laws we've been talking about, okay, looking at how pressure and volume and temperature change and relate to each other. We're going to focus on two of them at a time, okay, so just pressure and volume, or just volume and temperature, or just pressure and temperature, where that third variable, that third property is held constant. So for instance, let's put this up here. Let's start over on this side, kind of go left to right. One of the gas laws is Boyle's law. It states that pressure and volume are working inversely of each other. That means one goes one way and one goes the other. If volume is going up in a gas, then pressure goes down, and if volume goes down, pressure goes up. Okay, so pressure and volume go opposite ways of each other when temperature is held constant. In other words, temperature is not changing. If pressure is the thing that's not changing, we're looking at Charles's law, where volume and temperature are changing. These follow each other. It's a direct relationship. So if our temperature increases, our volume increases. If our temperature decreases, our volume decreases. And finally, if we're keeping volume constant, we're looking at Gay-Lussac's law, where if temperature increases, pressure increases, and if temperature decreases, pressure decreases. This is also a direct relationship. They kind of follow each other. Okay, so with these three gas laws, we're going to be trying to identify in each little mini experiment what is changing and what's not changing. Okay, and specifically we want to know what direction that change is happening in. So if I think that the temperature is changing, is it increasing or decreasing? Is it going up or down? If my pressure is changing, is it, again, increasing or decreasing? So it's not just enough to say, oh, pressure changes, but is it going to get higher or lower? So we're going to show an arrow, kind of like I've got up here, to show if it's increasing or decreasing. We'll pick a gas law that fits the two properties, the two variables that are changing, or at least most important in that station, because some of these are a little bit complicated. Sometimes all three properties seem to be changing at the same time. The real world is a little bit trickier than what we run in simulations and what we simplify in example problems. So we're going to pick what we think fits kind of best. So let's look at our first station. Down here. All right, so this is station 1. We've got a candle and a test tube. So this is our candle. This is sitting in a bath of water. I just colored it red so it's easier to see. I'm going to light a match. So I can light this candle. There we go. Put the match out. Okay, so the flame from this candle is heating up the air around here. I can already feel it getting hot. Okay, I'm going to cover it and suffocate the flame with this test tube. If you watch the water level inside here, okay, we end up sucking some of the water up, which is interesting. Sometimes if I lift it just a little bit, they'll suck it up even more, so you can really see that difference in liquid level. So what's going on here? Well, our temperature increased above the candle first, okay, but once it snuffs out and it's going to cool down, our temperature is dropping. So when I put the test tube over the candle and snuff out the flame, our temperature is going to decrease. Okay, our temperature is going down. Now, if I'm trapping the air inside this test tube, okay, this is pretty rigid. It's not going to flex. There's not a whole lot of room for the gas to escape and stuff. So we can kind of assume that volume is constant, at least for now. We can kind of see it like that. So as volume is not changing for that air, but our temperature is going down, the other thing to change is pressure. So our pressure inside here, the pressure of the air that we're kind of catching in here, as it cools down, should decrease. Okay, and you can figure out which gas law best fits that. If our pressure and temperature is changing, our temperature is dropping, and our pressure is dropping. Now, you might also interpret this in a different way. So let me say, I'm going to relight this. The candle's going to be a little bit wet, so it might not work. I have to dry that off a little bit. Okay. So these are not stuck to very specific answers. Sometimes you can argue a couple different ways for which gas law you're using or which properties are changing, especially because a lot of times we do something and then we reset the lab, so we kind of see it both ways. So in this case, you might be seeing this as the temperature goes up. Okay. And as the pressure therefore increases for this air above the candle, rather than focusing on how it cools down once you put this over. You might also say that yes, the test tube is rigid, but our volume of air is decreasing inside the test tube, so that could be a change in volume caused by the temperature change. So the drop in temperature is decreasing the volume of air inside here, and instead it's replaced with water. It's sucked up. Okay, so whether you're looking at the pressure decreasing inside here, where we don't have enough pressure to keep the liquid out, it goes up into the test tube, or we're looking at the volume shrinking, the volume of the gas in the test tube shrinking, either way would work. So you could go a couple different ways with that. Just make sure that you're consistent when you decide on which gas law you're picking and which direction your variables are going. Remember, Boyle's law says that our pressure and volume go opposite directions. Charles' law and Gay-Lussac's law say that those variables follow each other. So volume and temperature go the same direction, and pressure and temperature go the same direction. Okay, so that's station 1. It's out of the way. Right. This is station 2. Oops. We're going to get a soap bubble on a can and see what we can do with it. So I'm going to dip this in my soapy liquid so that the opening is covered with a thin soapy film. I want to basically be able to make a bubble over the top of this. Like that. Okay. So it's kind of hard to see. But I do have a bubble there. Okay, so I have a bubble over the opening there. All I'm going to do is I'm going to gently cup my hands over this. Alright, you can see the bubble changing there. Oh, apart. Okay, so it's maybe a little bit hard to see, but as I was cupping the can with my hands, the bubble was growing. It was getting bigger. Let's do it one more time. So I'm not squeezing the can. Instead, I'm using the heat from my hands. Let's see if you can see the bubble rising. There it is. Okay, I'm using the heat from my hands to increase the temperature of the air inside the can. Well, my bubble is getting bigger, so you could say that the volume is increasing as the temperature increases, or you might say that you have an increased pressure that is pushing the bubble up and expanding it. Either way, we're picking two variables that you think fit best to this situation. Okay. Now again, you could also look at this as the cooling down aspect. We can use a little bit of rubbing alcohol on the outside of the can and get it to cool down as that rubbing alcohol evaporates. Then we see the opposite effect. The bubble gets smaller and it actually goes back inside the can sometimes, which is pretty cool. So you could do it from that direction too. Either your temperature is increasing and therefore your pressure or volume is increasing, or we've got our temperature going down and therefore our volume or pressure is going to go down with it. But temperature is going to be one of the main factors we want to include there, from the heat from your hands or the kind of stealing heat from rubbing alcohol evaporating. Oops. All right, station 3 has to do with this bike tire back here. All right, so the stem for filling up the tire is right here. Well, actually, that might reach. Let's see. Yeah, I can do it. Okay, so right now the tire's pretty flat. Okay, I can squeeze it and show that. So I need to fill it up with some air. I'm going to fill it up to about 40 psi with this pump back here. Feel the tire stiffening up. There we go. So it's nice and pressurized. Okay, much better. Now, since the cap is off, it's going to start leaking, so you can probably hear that as the air is coming out here. I can also speed up the release of air by pushing on this little stem on the inside of the valve. So that's going to release air a lot faster. It actually gets very cold. Which is kind of surprising. Okay, so as we release the air, okay, our tire deflates. All right, and we have a pretty vast temperature drop. It's cold enough to notice, like, ooh, like that's cold. It's not just cool, it's cold. Okay, so we've got a temperature drop. Our temperature is going down, and you could say that is either due to the pressure inside the tire changing, okay, or the volume inside the tire changing. Again, you could kind of make an argument either way, but make sure you get the direction right, okay? If our temperature is decreasing, what is going to happen to the volume, or what is going to happen to the pressure? Is it going to go up, or is it going to go down? So be careful, think about it. Okay, so that's station 3. Station 4 is going to use a syringe like this. Okay, we need something to put inside it. What we're going to use is just a typical little mini marshmallow. Just happen to have a bag right here. I just need one of them. Place that down inside there. All right. I'm going to put the plunger back in. Okay, so there's the marshmallow down in there. A little bit. Okay, so keep an eye on the size of the marshmallow. I'm going to plug the hole so no more air can get in. And then I'm going to raise the plunger on the syringe and see what happens to the marshmallow. See that difference? I'm going to let it go. Looks all shriveled up. It's kind of hard to see from the glare on the table. Okay. So what I get out is this nice little shriveled marshmallow. Okay. with the plunger and the syringe, I start with a specific amount of air. Okay, and again, I don't let any in. Okay, so if I'm not letting any more air in, this is all I've got in here at the bottom. Okay, I'm plugging it up here. So if I pull the plunger like this, I am increasing the volume of that amount of gas. I'm not adding any more, I'm just increasing the volume of it. Let's see if we can move this here to kind of block the glare a little bit. That's a little better, I guess. Okay, so when I plug this up, pull up on it, okay, the marshmallow grows in size. It's kind of like a beating heart. All right. Because the pressure inside is changing. Well, my volume is increasing as I'm lifting up the plunger, and I don't feel it getting really any warmer or colder, so temperature is probably not changing here. So you can probably figure out which gas law is going with this. Okay, temperature stays constant, but pressure and volume are changing. So if you figure that gas law out and volume is increasing, what has to be happening to the pressure inside here? Okay, well, usually pressure and volume go opposite directions in this gas law. So if volume is increasing, then pressure should go down, okay? Which makes some sense. That's why our marshmallow gets bigger, because we no longer have that pressure holding it all together in its usual size. We let off on the pressure, and all of a sudden it can expand from all that air that's in between it. Okay? Now once that air escapes, then there's not really getting it back in. So if you do this a whole bunch of times, you will eventually get a marshmallow that does not grow all that much. It starts to get all shriveled and messed up because we keep sucking the air out and then can't really put it back in. So we get kind of this sad little shriveled marshmallow like that. Okay, so that is our marshmallow in a syringe in station 4. Got some more marshmallows escaping. Station 5 is going to be down here with this Bunsen burner. Okay, so I'm going to turn the gas on. Okay, and we're going to be heating up the water inside this test tube and seeing what happens when we make steam out of it. We boil that water, what happens to the balloon here on the end. So I'm going to back this up a little bit. Raise it up here. Got our gas flowing. Go. Watch this here. So our water's starting to evaporate. It's getting hotter and hotter. Soon enough, it's going to start boiling. There it is. You can hear the bubbling. Right, before we just had the liquid water in here and air, but now, as this water boils, we have another gas. We have steam. And that steam needs space. So as our temperature increases, as our temperature increases, something's happening up here. So what do you think? Is it the volume that's changing? Is it the pressure? If you think it's both, which one do you think plays a bigger part here? Which one should we focus on? Okay? If we let it cool down, our water is going to change back from steam, from water vapor, back into a liquid, right? And our balloon is going to start shrinking as a result. We won't have any gas to fill that space. We'll just have the regular air that was already in there. That's kind of hot. Okay, so that's station 5, heating up the gas in a balloon with steam. Kind of sad. Deflates like that. This is just kind of an extra fun thing. As the water vapor, the steam, cools down, it'll condense back into a liquid. Since the balloon kind of droops like this, if we give it some time for that water to condense, it'll usually collect in the balloon like this. So I'll have to kind of like lift the balloon up and dump the water back out to get it to run back down into the test tube. Okay, station 6 is going to be our mini vacuum chamber. Specifically, this is the mini vacuum chamber right here. Scoot it back a little bit. We just got sticky tack to the table so it doesn't move on me. It's got a hose coming out. All right, this is where we're going to suck the air out. This is my vacuum pump. It's got a pressure gauge on it. And the hose is connected to our chamber here. That around like that. Okay, so as I squeeze this handle, did you see that? Okay, this sucks the air out from the jar inside here, like that. And the pressure gauge tells me how much pressure I've lost. So, kind of turn this around. See if I can get it on the screen. Probably can't read that very well, but you can kind of see the dial moving a little bit. Let's speed this up a little bit. So as I suck the air out of this jar, you might be focusing on the air inside the balloon, which is the air kind of from the outside, or you might be focusing on the air down below the balloon, which I keep sucking out. So depending on your view of it, you could be looking at pressure of the air inside the bottom here, or pressure of the air inside the top here. But in either case, we don't really have temperature changing. So it should be pretty easy to figure out which gas law is kind of the major player here. And remember, in that gas law, our pressure and volume should go opposite ways. So we got to kind of make sense of it. If you're looking at the air inside the balloon, okay, versus the air kind of down here, it makes a difference. So you have to kind of be careful about that. Okay, but think about how the volume is changing and how that would affect the pressure. Okay, and vice versa. To release the pressure from the outside and to get some air back into the bottom, I just have to lift the edge of the balloon. There we go. It fills right back up. All right. Now, we've got one more station that's a bonus station. Usually there are a couple options, but I'm just going to pick one of them to throw in, the one I think is usually the coolest. Okay? So we've had 6 stations here. This is our mini vacuum chamber. And then we've just got one left. That's our bonus station. Okay, and this is one of my favorites, just in general. Okay, this is what we call the hand boiler. Right now, the hand boiler is a little bit of a misleading name because by the sound of it, it sounds like you can use your hand to make the stuff inside boil. Okay, the way I'm going to do this is use my hands, and I'm just going to cup around it, kind of like I did with the can. And I've got my liquid moving up through this kind of glass straw here. Until it reaches the top. Starts to fill it. And then once I've got all the liquid up there, we can get to the part that looks like the boiling, where it starts bubbling, where it's like, ooh, okay, well maybe the liquid's boiling, maybe it's turning into a gas, okay? But not quite. It's not really hot enough for this to be boiling, or else I would probably be in trouble, okay? My hands provide some heat, but not that much heat, okay? What's going on instead is a little trick with air. So we got the straw that extends down into the bottom here where we have this pool of liquid. Okay, the heat from my hands is going to move into the glass here and increase the temperature of the air inside this apparatus, this little glass bulb. Okay, as that temperature as that temperature goes up, as the air gets hotter inside here, well, this is glass, it's pretty rigid, so our volume of our gas isn't really going to change. It has nowhere else to go. So if our volume isn't changing, but our temperature is, the only other thing that can change is the pressure. So our pressure must be changing here. One of your gas laws says that if temperature is changing one way, the pressure has to go with it the other way, as long as volume is constant. Okay? So, I might have said that wrong. Temperature is increasing. Pressure has to be increasing with it. Okay, they have to follow each other. It's a direct relationship. So if I said the other way, that might have been backwards. Okay, so if my temperature of my air is increasing in here, my pressure has to be increasing with it. Okay, our particles are moving faster and faster and faster, and therefore pushing harder and harder and harder on the surfaces inside here and also on the liquid. Okay, so what ends up happening is our air that is now at a higher temperature and therefore a higher pressure is going to push down on the liquid more, and the liquid has nowhere else to go except up through this straw. Okay, so as we continue to give it heat, the air pushes down on the liquid therefore escapes to the only place it can go, which is up through here. And what we see as the boiling is actually just the air coming after the liquid. Once we have kind of pushed all the liquid that we can through and up into this top bulb, well, the pressure and temperature of our air down below is still increasing, so it's going to start pushing its way in too. It's got to find some more room, so it will go wherever it needs to. In this case, it's going to go up that straw just like the liquid did, which is why it looks like it's boiling. Okay? In reality, it's just the air at a higher temperature and pressure that's pushing and forcing its way through the liquid. I can also heat up the top here and get the liquid to fall back down to the bottom, which is pretty neat. Okay. One last little trick that is just kind of extra. So I've got some rubbing alcohol here. I mentioned that we can use the rubbing alcohol to cool down the can. As it evaporates, it seals heat from the stuff around it. Okay, so let's say that I've got this all the way down to the bottom. Okay, I can even kind of like push the air through the bottom too. It's going to start boiling, so-called boiling down there. Not really. If I cool off the top here, putting some rubbing alcohol on it, and therefore cooling it down, okay, that's going to reduce the pressure up here, which means that kind of in comparison to the air down here, it's now pushing harder. Okay, if I wanted to stop it and make it go the other way, I could cool down the bottom. So in this case, rather than adding heat, I'm removing heat. So if I remove heat from the top, it's kind of like adding heat to the bottom. My temperature is kind of higher, my pressure is higher down here. Okay, and if I steal heat from the bottom, again, it leaves the top set of air kind of higher temperature, higher pressure, and then our liquid moves. Okay, so that's our kind of extra bonus station, the hand boiler, and that gives us a good survey of the different gas laws and different demonstrations of those gas laws. So hopefully those made sense, and if not, you can kind of go back and rewatch them, see which variables are changing, and again, make sure you try and match it up to the gas laws as best you can. So see which kind of fits best, Boyle's law, Charles' law, or Gay-Lussac's law. Okay, changing pressure and volume in opposite directions, volume and temperature in the same direction, and pressure and temperature in the same direction.